Hello friends, welcome back to this series where we work through and explain the book on quantum mechanics by Steven Weinberg. We are now at part 6 of chapter 4, which is all about spin and angular momentum. Today's topic is the famous Wigner-Eckart Theorem, which is a very general result due to Eugene Wigner and Carl Eckart. It has to do with the matrix elements of a family of operators that possess well-defined rotational properties. These matrix elements are important because they appear in the calculations of transition probabilities of systems that are governed by Hamiltonians that have rotational symmetry. These include transitions in an atom, which give us the spectral lines. This theorem is the culmination of the results on the rotation group, which we have developed over many lectures. Without further delay, let's begin. The matrix element we are talking about looks like this. OJM is an operator that rotates like the angular momentum states Jm. What we mean by this will be clear in a minute. Note that we are really talking about a set of operators forming an angular momentum multiplet, much like the J multiplet. The two states that form the bracket are also angular momentum eigenstates. The Greek symbol in front always represents all the other quantum numbers that are not affected by rotations, which are not shown explicitly. The Wigner-Eckart theorem states that this matrix element must be equal to the Clebsch-Gordan coefficient, which connects the three angular momentum states, multiplied by a term that consists of all quantities that are invariant under rotations from the states and the operator. This is known as the reduced matrix element. All rotational properties are captured in the Clebsch-Gordan coefficients. These are discussed extensively back in lecture 21. Check out that video if you need a reminder. The link is in the description below. The intuition behind this theorem is that the operator OJM acting on the state psi behaves as if it is the product of angular momentum states Jm and J'M'. As long as the operator rotates like Jm, this is the key. And from the development in lecture 21, we know that any angular momentum state like J'M' in our case can be expressed in terms of two lesser angular momenta, J and J', through the Clebsch-Gordan coefficients. This product basis is chosen such that the state in the red box is one of the elements. Of course, it is always understood that the other quantum numbers could also be present, which are not written explicitly, and which are captured by phi, psi, and O in the reduced matrix. Using the orthonormality of the angular momentum basis, it is therefore not surprising that the Clebsch-Gordan coefficient appears in the expression for the matrix element above. This coefficient is simply the inner product between J'M' and the product state Jm, J'M'. In writing this, we have assumed that these coefficients to be real. This is consistent with our convention in lecture 21. Here's a reminder about how two angular momentum states can be combined into one from lecture 21. All these angular momenta are connected through the relations underlined red. Now we shall explain the key point to the proof of the Wigner-Eckart theorem. What does it mean to say that the operator OJM rotates like the state Jm? Recall how an angular momentum state rotates. It is transformed by a unitary operator which represents the rotation. R is the rotation matrix of vectors in three spatial dimensions, the kind of rotations that we are most familiar with. The generators of rotations are just the total angular momentum operators of the system. And by specifying how these operators act on the state, will determine how this state transforms under any rotations. Let's express this transformation in the basis of angular momentum states by inserting some identity operators. Since the action of the angular momentum operator J could never bring a state Jm out of a J multiplet, we can effectively ignore all the basis elements that belong to the other multiplets and just keep the J multiplet. To keep things concise, let's hide this quantum number. After all, it is just going to be a constant throughout all our manipulations. This bracket is just a Kronecker's delta, as the basis is orthonormal. Let's notate this matrix element by a square bracket. Thus, by specifying the matrix in the blue box, we will be able to describe the action of the generator J on any state in the J multiplet. To be clear, let's write the quantum number J explicitly just this once. Actually, the matrix below should also be labeled by J, but we shall omit it as long as this is clear from context. Instead of looking at the effects of the Cartesian components of the angular momentum operator, we could as well look at how the angular momentum ladder operators and J3 act on quantum states. Since these two representations have a simple linear relation, knowing one of them is as good as knowing the other. Therefore, how the Jm states are transformed by rotations are also entirely determined by how they are transformed by J plus minus and J3. We have worked these out in lecture 20. For OJM to rotate like the state Jm, let's use the most straightforward construction. Let the operator X on the state that is rotationally invariant, a state with zero angular momentum, such that OJM carries all the rotational properties of the resulting state, and we require this state to transform in exactly the same way as the state Jm under rotations, which is to say that it must transform according to the rules above under the action of J3 and J plus minus. Let's see what it means for the first condition to be satisfied. The operator OJM must satisfy this equation. We can write this in terms of the commutator between J3 and OJM. Note that J3 acting on the zero angular momentum state just gives 0. This leaves just the commutator. The last equation can be satisfied for any zero angular momentum state if we insist on this commutation relation. With this equation, we say that the operator OJM transforms under J3 in the same way as the state Jm. Now let's do the same for the second condition. Note again that the zero angular momentum state, being invariant under all rotations, must give zero under the action of all rotation generators. By the condition above, this must be equal to. These two states are analogous. Once again, we can see this as a condition on the commutator. These commutation relations are what we meant when we say OJM rotates like the state JM. We could condense these transformation rules of the JM states into a single equation as we did earlier. We could also do the same for the commutation relations. This is the direct consequence of the equivalence in the yellow box. Let's write down the matrix elements that correspond to these commutation relations. The matrix of J straight is simply a diagonal matrix with values h bar times m. Now for the matrices of J plus minus. These matrices, together with the commutators with the rotation generators J's, completely determine how the operator OJM transforms under rotations. Let's go back to how the JM states themselves transform. In terms of matrices in the angular momentum basis, this can be written as, where the matrix of UR is given by our earlier convention. This matrix is obtained by just the substitution of the matrices representing J into the standard exponential form below. We now prove that the operator OJM rotates by being sandwiched between U and U dagger, and this must be equal to the same U matrix that transforms the states JM. By establishing the result in the green box, we can prove once and for all the equivalence in the yellow box in terms of how these two states rotate. As mentioned before, this equivalence is the key to proving the Wigner-Eckart Theorem. We claim that if these two exponentials are expanded in a power series, we would end up with a series of increasingly nested commutators like this. For this to work, it is important that the ordering of all operators is maintained throughout the expansion. It turns out that this series sums back up into another exponential with a commutator that has an empty slot in the exponent. This slot is supposed to be filled with the operator OJM in increasing order of nested commutators as the exponential function is expanded in a power series. Here's an exercise that will help you derive this result. Prove this operator identity. Let's look at the power series of this exponential. This notation is just a convenient way of expressing the nesting of the commutators around the target n times. Here's a hint to help you proceed with this problem. Let's introduce a parameter lambda and expand this expression in terms of lambda in a power series, taking care to always preserve the ordering of operators. The answer to this exercise will be discussed in the next video. We now go through a few of these terms, and you will immediately be able to see the general pattern that emerges. First, for n equals 0, this is the case with no commutator, just OJM. Next is n equals 1, with one commutator. We can evaluate this directly using the commutation relation in the blue box. Here, let's use the Einstein's convention, where repeated indices are summed over, so that we don't have to keep writing summations. And now for n equals 2. Once again, we can use the blue box. It is helpful to note that the index of O in the commutator is always carried by the second index of the resulting matrix. We can see that the matrices that resulted from each commutator are multiplied together, with the foremost index contracted with the one carried by O. O is always the only operator left, with the rest of the terms just numbers. So basically, if we nest this expression within another commutator, the blue box can be used once again, and repeatedly at higher orders. For order n, the pattern just continues. The result of the nested commutators is just n matrices of the rotation generators multiplied together and contracted with O. As you can see, this series sums back up into an exponential matrix, which is of course just the unitary matrix U, which represents rotations in the angular momentum multiplet J. This angular momentum matrix is the same as the one in the commutation relation in the blue box. Thus, we have proven the identity that we have set up to prove. This identity is useful because it allows us to work out how the state which results from OJM acting on the zero angular momentum state transforms under rotations. It is apparent that this rotation rule is exactly the same as those for the Jm states. With this, the equivalence of the two states in the yellow box under all rotations is established. This is what we meant when we say OJM rotates like the state Jm. As we can see, this result is the direct consequence of the commutation relation above. It is important to note again that the numbers Jm merely captures the rotational properties of the operator O. This equation is actually very general and could contain many other quantum numbers that are invariant under rotations. Now we can finally take the last step to complete the proof of the Wigner-Eckart Theorem. Let's see what happens when OJM acts on an angular momentum state that has non-zero angular momentum. From our earlier discussions, we could expect this to be a product state of the two angular momenta, one associated with the operator and the other the state, plus some additional quantum numbers that are invariant under rotations. If we can prove this relation, then this product state could then be one element of a basis for a total angular momentum state that is an eigenstate of the sum of the two angular momenta. And at this point, the Wigner-Eckart theorem is as good as proven. Therefore, our task now is to demonstrate this equivalence. All we need to do to prove the equivalence of these two states is to show that they transform in the same way under the action of J's ray and J plus minus. This will imply that they rotate in the same way. For now, let's just focus on the angular momentum of psi and ignore all its other quantum numbers. First, let's look at the action of J's ray. For this term, we can use the commutation relations satisfied by OJM. This is exactly how J's ray will act on the product of angular momentum states. Now let's see the action of J plus minus. We can now use the second commutation relation. Let's use the notation we have used back in lecture 20 for this numerical factor, which is basically just a normalization factor after raising or lowering with the angular momentum ladder operators. Again, J plus minus has an identical effect on both the operator O and the angular momentum state. Once again, it is as if J plus minus is acting on the product of two angular momentum states. With these results, we have thus proven the equivalence of the two states in the green box. Let's apply this result to the matrix element in the Wigner-Eckart theorem. The constant associated with this proportionality carries all the rotationally invariant quantities associated with the operator O and the two states of the matrix, phi and psi. Of course, these also include the quantum numbers J double prime, J, and J prime. This constant of proportionality is the reduced matrix element. It is independent from all the variables that are affected by rotations, like m double prime, m, and m prime. Of course, we could substitute this inner product with the Clebsch-Gordan coefficient in accordance with the rules of addition of angular momenta. This is the Wigner-Eckart theorem. It is the direct result of the commutation relations with the rotation generators of the operator OJM. As mentioned earlier, these operators come together in a set of 2j plus 1, which are components of the j multiplet, and they transform into each other under rotations, as can be seen in these commutation relations. Hence we call this a spin j operator. Personally, I find the inner product more descriptive than the Clebsch-Gordan coefficient. Now we look at some examples of spin j operators. Let's start with j equals 1, which has three components corresponding to m equals minus 1, 0, and plus 1. We can work out all the commutation relations according to the white box below. Starting with those involving J's ray, this is easy because it just returns the same component in the commutator. Now the commutator of J plus minus with V0, which raises or lowers it to V plus minus. Now raising and lowering the plus 1 component. Of course, we can't raise it any further because this is the highest weight, but lowering gives us V0. Now raising and lowering the -1 component. This is the lowest weight, so lowering gives 0. And raising gives V0 once again. For completeness, let's include the raising of the highest weight and the lowering of the lowest weight. Both give 0. These commutation relations determine how the components in the j equals 1 multiplet rotate. They are components of a vector operator in the spherical basis. What about the components of a vector operator in the Cartesian basis? This is the form of the vector operator we are familiar with from lecture 19, which satisfies the commutation relation in the green box. How are the components in these two bases related? You can work this out in this exercise. Find the Cartesian components of the vector operator V in terms of its spherical components above. They have a linear relation with each other, where the omegas are constant coefficients. VI's should satisfy the commutation relations of Cartesian components. Use the commutators for the spherical components to show this. And just to remind you how j plus minus are defined in terms of the Cartesian components. The solutions to the exercises in this lecture will be discussed in a separate video. To be clear, this subscript of the spherical components always refers to the angular momentum multiplet to which they belong. And of course, this relation between the Cartesian and spherical components is invertible since the bases are equivalent. The matrix omega connects the components of the Cartesian basis to the spherical. In a similar way, the familiar Cartesian components of the angular momentum operator are related to its spherical components with exactly the same matrix omega. These spherical components are equivalent to j stray and j plus minus up to only the normalization constants, which just means that their commutation relations may be superficially different. You will find out all about these in the exercise just mentioned. With these results, we can demonstrate a remarkable consequence of the Wigner-Eckart Theorem. We begin by looking at the matrix element of the angular momentum operator. Let's write this in terms of the spherical components. Applying the Wigner-Eckart Theorem. Let's keep this result for reference. Next, we look at the matrix element of Vi, which is the Cartesian component of an arbitrary vector operator. In exactly the same steps as before, we can express this in terms of the spherical components, then apply the Wigner-Eckart theorem. Looking at this term in front, which is a generic, rotationally dependent term, and comparing with the result in the blue box, we have this term in the yellow box just contains all the other details about the states and operators in the matrix element that are rotationally invariant, which leads us to this remarkable result. The matrix element of any vector operator, where the two states involved are eigenstates of angular momentum multiplets, is proportional to the same matrix element of the angular momentum operator, up to a rotationally invariant constant. This is a remarkable result because there are literally an infinite number of vector operators, and they are all proportional to this particular vector j. This general result will prove useful in future chapters. There's one more thing to say about this result. It is not difficult to see that the quantum number j for both states in this matrix element must be equal. This equation implies that unless j double prime is equal to j prime, the matrix element must be equal to 0. This completes our result. In our next example, let's look at what the Wigner-Eckart Theorem has to say about atomic transitions, specifically the selection rules that govern whether a transition between two energy levels in an atom is favored or not. Any transitions that violate selection rules will be greatly suppressed. The transition rate from an initial atomic state A to the final state B is given by the absolute square of the matrix element of the interaction Hamiltonian that corresponds to the states A and B. This formula is an example of what is known as the Fermi's golden rule. Given any interaction Hamiltonian that drives a process, it provides the leading order approximation to the rate of quantum transitions. We shall give a detailed derivation of this rule when we get to time-dependent perturbation theory in quantum mechanics. That's chapter 6. In the meantime, you'll just have to take my word for it. This formula is the reason why we keep mentioning the matrix elements of operators. The relevant Hamiltonian for atomic transitions, which gives us the spectral lines, is the coupling of the electric dipole moment with an external electromagnetic wave. This is the light wave that stimulates the transitions. The unit vector E is just a polarization vector of the electromagnetic wave. This is just a number vector, while the electric dipole is an operator that is composed of the observables of the electrons in the atom. This picture should illustrate the situation. The dipole moment of the atom is defined by the sum of the products of the electric charge and the position of the particles in the atom relative to its center. The positions, of course, are operators. How this operator enters the picture of atomic transitions will be discussed in chapter 11, which is all about the quantum theory of radiation. There's also a condition we have assumed in writing down the Hamiltonian for the dipole transition of the atom. The wavelength of the electromagnetic wave is assumed to be very much larger than the size of the atom, such that the electric field that couples with the dipole is effectively uniform. And the direction of this uniform field is just a polarization vector. Once again, let's express the dipole moment in terms of its spherical components. The matrix element of H interaction is given by, and we again have the matrix element of the spherical component of a vector operator. This would be ripe for the application of the Wigner-Eckart theorem. Let's assume that the states A and B are angular momentum eigenstates, which are of course what the electron orbitals are in atoms. This means we can apply the Wigner-Eckart Theorem. By the rules of addition of angular momenta, we have the following conditions for this inner product to be non-zero. These conditions are derived in Lecture 21. Let's rewrite them in a way that makes it clear how the quantum numbers of the states A and B are restricted by these conditions. Let's start with the second equation about the magnetic quantum numbers. The absolute value of m must be less equal to 1 according to the range of m above. Remember that this is a quantum number of the electric dipole moment. This restricts the absolute difference between the magnetic quantum numbers of the states A and B. Next, let's see how these inequalities constrain JA and JB. Let's start with the first one. Looking at this absolute value, there are two possibilities. The first is when JA is greater or equals to 1, which means the inequality becomes. This implies. Now look at the second inequality. This implies. Therefore, these two inequalities have to be true at the same time. Their left-hand side is just the negative of each other, which means the absolute value has to be less equal to 1. Now we go back to the second possibility of the first inequality regarding the absolute value. JA less equal to 1, which means the inequality becomes. This implies. These conditions are an alternative way to express the rate box. In this form, it is much easier to see how the angular momentum quantum numbers of the states A and B are constrained. These are the selection rules that have to be satisfied in order for the matrix element of the electric dipole operator to be non-zero. They are the direct result of the Wigner-Eckart Theorem. The leading contribution to the transition rate from the atomic states A to B is only non-zero if the selection rules in the rate box are satisfied. As we can see from these rules, this process does not necessarily conserve the angular momentum of the atomic orbitals, which is expected since the photon that is emitted or absorbed during the process can also carry angular momentum. The processes we are modeling are known as electric dipole transitions, or E1 transitions. The 1 just refers to the j equals 1 quantum number of the dipole operator. We shall have more to say about this in Chapter 11. What are the other operators that form an angular momentum multiplet? Here's a less trivial example involving integer values of j, which corresponds to the spherical harmonics. Recall that these are eigenstates of the orbital angular momentum. We have discussed this extensively in Lecture 11. Check out that video if you need a refresher. The link is in the description. Let's look at the position space wave functions of these states. As we have seen in Lecture 11, these functions depend only on the direction of the position vector. Let's denote this unit vector by x hat. So where does the operator OLM come in? Now here's the claim. If we substitute the direction vector in the spherical harmonics by its operator representation, we will have a set of operators that form an angular momentum multiplet that have the same quantum numbers as the spherical harmonics, which satisfy the commutation relations below. It is actually not difficult to see why this is true once we know how the spherical harmonics themselves transform under rotations. For a start, let's show that these operators satisfy the first commutation relation. We start by remembering how the third component of the orbital angular momentum, L3, acts on the spherical harmonics. Using the eigenvalue equation, to work out the left-hand side, just use the position space representation of the position and momentum operators in the definition of angular momentum. Let's turn this into an operator equation by replacing the position vector with operators. This shouldn't be a problem, because the different components of the position operator all commute with each other, and therefore there's no issue of ambiguous ordering of operators. Let's look at the term in the red box. Recall that back in Lecture 2, we have demonstrated the product rule of commutators and how this could look like a derivative when the commutation relation between position and momentum is applied. F can be any function of the position operator. Let's use this identity to write the derivative in the red box as a commutator. We can bring in the position operator into the commutator together with the momentum operator, since it commutes with the argument of the spherical harmonics, and also the epsilon symbol. This completes our demonstration. Thus we have shown that the operator YLM has indeed the right commutation relation with the third component of angular momentum, L3, to be an operator of spin L. This is directly implied by how L3 acts on the spherical harmonics wave function. Demonstrating the second commutation relation is basically an identical story. This next exercise will help you work through it. Prove the commutation relation in the red box and complete the demonstration that the operator YLM is indeed a spin L operator. Use these properties of the spherical harmonics to help you. We shall go through the solution in the next video. Now that we have shown that the spherical harmonics, with its position argument replaced by the position operator, is indeed a spin L operator which satisfies these commutation relations, we can take another simple step to make this result even more general. Notice that these commutators on the left-hand side are fully determined by the commutator between L and X. And since the position operator is a vector operator and rotates like one, this commutator is just equal. This is the commutation relation for the Cartesian components of a vector operator, which is equivalent to an L equals 1 operator in the spherical basis. Imagine if we replace X by V, which can be any vector operator. The commutators in the red box will just run its course, being fully determined by the commutation relation in the blue box, and in an identical way as for the case of x. So the result on the right-hand side will simply be the same expressions as before, but with x replaced by v. Thus any vector operator which satisfies the relation in the blue box will automatically satisfy the relations in the white box, which is to say that substituting any vector operator into the spherical harmonics YLM will give a spin L operator. In fact, even if we multiply this by a rotationally invariant operator, for example, some function of the magnitude of a vector operator, the resulting operator will still be a spin L operator and satisfies the same commutation relations, since the rotationally invariant operator will simply commute with all generators of rotations. If you like this video, consider giving it a like and subscribe to this channel. And remember to press the notification bell so that you'll know when a new video is ready. See you next time, and thanks for watching.